This is a short tutorial on randomness and uncertainty. I'll be using Python language to demonstrate certain concepts related to randomness and uncertainty. The first question is, why should we even study randomness and uncertainty? So the answer to this is that practically everything that's happening in nature and around us is random in nature. Whether it is weather change or switching on and switching off of traffic lights, arrival of customers at a store, lottery drawings, radioactive decays inside an atomic bomb, or arrival of emails, or sporting events and their outcomes, or stock market, or birth of triplets and twins. Anything that you can think of which happens naturally is random in nature. And the reason why we should be studying randomness is that there's a basic human desire to know things so that they become predictable. And once they become predictable, we can control them. Humans have a deep desire of controlling things, and that can only happen if you can predict the event, if you have some knowledge about the future inferences. So that's the reason why we should be studying randomness. Firstly, it's prevailing all over, and secondly, we have a deep desire to control things. So that's out of the way. So before we go to randomness and uncertainty, let's understand what is determinism and certainty. So for demonstrating this, I will define a timeline. And using this timeline, I will create a data, and I will show you that what is predictability and what is determinism. So I start off with defining a time, which is going to start from 0 seconds to 32 seconds, and I'm going to be creating 10,000 data points. So the next point is to create a deterministic signal. So here I have created a signal called y1. You can call a signal as data as well. And I'm going to plot it and see how this signal looks like. So there we are. Let me just explain what we are looking at. So on the x-axis, we have time, and we have just created our future from 0 seconds to 32 seconds. And on the y-axis, we have some data which is varying from -1 value to +1 value. And as you can see that there is a pattern in this data. If you see this shape, which starts from 0 and again ends at 0, this basic pattern repeats. So again, it repeats from here to here, and then again from here to here, and again from here to here. So if we know the basic pattern in the data, then we can predict what's going to happen in future. So I just need to know what's happening in the first probably 5 seconds or 6 seconds. If I know this much, then I just need to attach the copies of this data, and I know exactly after 30 seconds, 50 seconds, 60 seconds, what the value of data is going to be. And that gives me a lot of predictability. I can see in future, and if I can see in future, I can control things. If it is desirable, I will try to apply certain kind of reward to the signal. If it is not a desirable signal, I will try to control it to do course corrections. And this is what is a non-random deterministic signal or deterministic data. Basically anything which is having patterns. So now we try to understand what is random data, what is non-deterministic data. So for that, I create another set of data. I call it y2, and as you can see, these are all randomly generated data points, 10,000 of them. And I will plot them again on the time axis, that is 0 to 32 seconds, and see if I can find some kind of pattern in this data. So here I am plotting this data, and let's see how it looks. So again, this is the time axis, 0 seconds to 32 seconds. And here is the data which is varying from almost -3 to +4. And I can't see any pattern in this data. Just because a value of around 3.8 or 3.9 has happened here, I cannot guarantee when this value will occur next. And that is the source of uncertainty. And if the signal is non-deterministic, can I do something to infer some information out of it? Basically, I've not been able to figure out any pattern. And because I've not been able to figure out any pattern, I'm not able to predict how this signal is going to behave in future. But still, all battle is not lost. There are a lot of things that we can do even in this chaos and randomness. And let's try to understand what can be done. So even in this randomness, there are a couple of things that you can observe. And what we observe from this data, actually, if you see, there are inferences that we can draw. Firstly, we can draw a very quick inference that if you draw a line at 0, this whole data gets evenly split into upper half and lower half, which means that the data has a tendency of centering around this 0 axis. And 0 axis, or the 0 value of data, splits this data symmetrically in the upper half and in the lower half. So that's the first inference that we can draw. Secondly, we can see that this data is swinging wildly between -2 and 2, and some of the values are extreme. Some of the values are going up to almost 3.8, 3.9, like this one, and on the other extreme, it is swinging way past -2.5. So there is a spread around this 0 axis, and that's the second inference that we can draw. Let's see how to make better guesses and inferences from this data. So we understand now that even in randomness and uncertainty, we can look at where the data is having the tendency to centrally aggregate, which is what is called an average. And we also can, by looking at the data, we can figure out that how much is the spread of the data. That gives us at least some insights into the randomness of the data. So let me just reconstruct another signal here, where I'm going to be using a different, axis. Instead of 0, I'm going to be using 10, and I'm going to be using a very different spread of the signal. And you'll see that how this signal behaves. So here we are. This orange is the new Y3 signal or Y3 data set. Again, we are measuring data from 0 seconds to 32 seconds. The blue was my original data, which was centered around 0 and was swinging between plus minus 2.5. This orange signal is entirely different. You can see that this is centered around 10. If we draw a line at 10, a horizontal line, the upper half and the lower half of the signal will almost be symmetrically split apart. So we can draw a conclusion that this data is centered around a value of 10, which is what is called mean or the average value of this random data. We also see that this data is swinging wildly. While most of the values are around maybe 17 positive side and around 5 or 4 on the negative side or the downward side, there are some extreme values which are swinging up to almost 23, 24. There are certain things like that. So definitely this data is more spread out in vertical axis, and this has shifted up by 10 in comparison to this original data that we had, that is blue. So if we can extract this information about the average and the spread, at least it gives us some more insights into the randomness, and we can start drawing more inferences and more actionable insights into the data. So just because it is random, that doesn't mean that we can't draw inferences out of this data. Let's move further. So what I intend doing now is that I talked about spread. So let me divide this spread into certain thresholds. Specifically, I'm going to be splitting these thresholds into 3 parts. I'll be setting 3 thresholds, and I'll be seeing how much this data is contained within these thresholds. So my first threshold will be positive threshold 1 and negative threshold 1, which is swinging around the average, that is the number 10, and it has some value on the upside and it has some value on the lower side. And then I'm going to be using a different threshold, which is slightly larger, a bigger one, and this time I'm going to multiply it by 2. So that becomes my positive threshold 2 and negative threshold 2. And then I'm going to be deciding a third threshold, which is even larger because I'm multiplying it by number 3. And let's see what these thresholds they look like. So here are thresholds are. So my positive threshold 1 is from value 14 to value almost 6, and threshold 2 is from 18 to almost 2, and threshold 3 is from positive 22 to minus 2. So let me just plot these thresholds on the data set, and it'll give a better visualization, and we'll be able to understand what's happening. So I have taken the same orange data, which is Y3. I've plotted it in another plot. Again, we have data from 0 seconds to 32 seconds. And now you can clearly see these thresholds. So on the y-axis is the value of the data, and on the x-axis is the time, obviously. So these black dotted lines are the first threshold, these narrow band. This is positive threshold 1 and negative threshold 1. And it is containing this mean. The central axis, which is splitting this data set symmetrically on top and at bottom. These thresholds are strategically placed so that they are around at equidistance from the mean. So that's threshold number 1. And then I said that I multiplied this threshold and widened it by a factor of 2, which is this red dotted line, red dashed line. And the last one is this green, which is multiplied by 3. So these 2 lines are having even a wider gap. So what I'm trying to do here is that by defining these thresholds, I'm trying to say, or trying to find out how much of the data points they remain within black threshold, that is threshold number 1, this gap. How many times the data crosses this threshold, but is limited to the red threshold, that is this these red dashed lines, and how many times this data is crossing the values above red lines on both the sides, positive side as well as the negative side, and is going beyond the green line. So this is what I'm trying to attempt here, to draw more information and inference into the data set. So let's see how I can infer that. So essentially, I'm going to be now counting the number of times the data has remained within a certain threshold. So we initialize all the 3 counts at 0. And then we are going to one by one count how many times the data has remained within the 3 thresholds that I discussed. So here is the first count, number of times that the data stayed between negative threshold 1 and positive threshold 1. And then next line of code is basically telling us how many times the data remained between negative threshold 2 and positive threshold 2. And lastly, how many times the data remained between negative threshold 3 and positive threshold 3. And I'm going to then count these numbers. So as you remember, right in the beginning itself, we had generated 10,000 data points. So now we are trying to figure out the number of times or the count of data which is divided over the threshold, 3 thresholds. So these were our threshold, three thresholds: 13, 6, 17, 2, 21, and -1. And the first threshold, that is this one, within this threshold, the data remained 6,821 times. In the second threshold, which is from 2 to 17 or almost 18, the data remained 9,551 times. And lastly, in the bigger threshold, the green one, which is between 21 to -1.94, the data remained 9974 times. So one inference we can straight away draw that the wider the threshold, the more data we will be able to find in that threshold. The narrower the threshold we've set, the lesser the data that we are going to find in that threshold. So once we have got this count, can we do something better? Idea here is that can I find out what is the frequency with which this data is falling in all these three thresholds. So I just have to do nothing much. I know that in the threshold 1, this data has fallen 6,821 times, and I just need to divide it by the total data set that I generated, which was 10,000, and that will give me the frequency, or also called the probability of this data being in this band. So that's what I'm going to do here. I took the counts and then divided them by the total number of data points that I have, which is 10,000, here right in the beginning itself. And that will tell me how frequently this data is falling in the three threshold bands that we chose. So here we are. So how to interpret this data? So we have data which is taking value between 14 to 6, and we can very confidently say if we randomly pick up anything which is falling between 14 and 5, for example, say number 8, then we can very confidently see that say that we can see such kind of data in the data set with almost 68% probability. So that gives you a deep insight into data, that if the probability of finding a value of y which is lying between 14 and 9 is 68%. So now we are talking in terms of probabilities. Now we are talking about how to eliminate uncertainty. This gives you at least some information. Even in randomness, this gives us some information that there is a 68% probability that the data will vary between 14 and 6. Moving further, in the threshold 2, which is a wider one, we can very confidently say that there's a 95% chance or 95% probability that data will assume a value between 18 and 1. It can be any value. It can be 10, 11, it can be 3. So that probability is 95%. And lastly, if we just further widen the band, we can very confidently say that the probability of finding my random data falling in this particular threshold, that is from 22 to -2, is almost 99%. So you try to understand what's happening here. Even in the randomness, even when the things are uncertain, I'm able to draw out some probabilities, which is giving me some fair idea as to how this randomness is spread out, how this randomness is varying. And this can at least give me some actionable information to design my system to take corrective actions. So I hope you've been able to comprehend it. This is how it looks in time domain. That means the x-axis is time, and this is the data values. The data can be anything. It can be height of men in a city, or number of academic courses that somebody has done after graduating, etc. That can be data, and over a period of time. So then, what is bell curve? This doesn't look like bell curve. Surely this is not bell curve. This is what is called as the time series, because the x-axis is time and the value of data is on the y-axis. Then what is bell curve? Bell curve is another interpretation of this data. There's another way in which we can look at this data, and let's see what that is. So we can calculate probabilities by specifying thresholds. Let's extend this idea further. So bell curve is nothing. Instead of just restricting ourselves to 3 thresholds, let's define more thresholds, a number of them, in a very narrow band, and calculate the counts of how many number of times the data is falling in those bins. So let me just activate this code. So just to give you a sense, I have, instead of 3 thresholds, I have taken 100 now. I have defined bins, and I'm just seeing that how many number of times a data fall in a particular bin. And then I'm associating a probability to that particular bin. In exactly the same manner, for example, if my bin is from 10 to 9, data assuming a value 10 to 9, I see how many number of times the data has fallen in that bin, and then I'm going to divide it by the total number of data points that I have, 10,000. That gives me the probability of data falling in that particular bin. So let's try to see this, what is happening here. This is an alternate way of looking exactly at the same data. This was the time series, and this axis was time. Now we don't want to see it in time. We want to evaluate this data in terms of probability. So what I have done is, this axis, which is the value of data, the magnitude of data, y3, I have taken this y-axis and I have plotted it on the x-axis now. So this is, as we saw that, data was centered around a value 10. The mean of the data was 10. So you can see here that the data is centered around 10. Now, what this axis is, this is no longer magnitude. This has been replaced by the probabilities that I've calculated. So when I talked about bins, earlier I just took 3 thresholds. I divided the data into just 3 thresholds. This green lines, this band which is signified by this red dash line, and this black band. I have extended this idea, and I have divided this data into small bins. Say, for example, I define a bin which is from 10 to 11. A data, how many number of times the data is between 10 to 11, for example. and I have defined a probability to it, and then I've sketched that probability here on the y-axis. When I do this, a very peculiar shape appears, and this shape, so the orange curve that you see in the underlay is called histogram, and the red line on top of it that you see is the curve fitting or the probability distribution of this particular data. And that's how it derives its name. This looks like a bell. And what it means is, it's plain and simple. What it means is that even if you have a data which is randomly varying, the probability of you finding this data at its center value, at its average value, is the highest. That's what it means. So you can see that at the data value 10, this is the mean which is passing through the center of this data set, splitting it symmetrically in top half and bottom half. So you will find that this randomness is contained or has a tendency to cluster towards its mean. And this is a very good information. This is very insightful. If you can find out the mean, then the probability of finding any random value closer to the mean is much higher than in comparison to some wild values like this. This value is wildly swinging on the negative side, and this value is wildly swinging on the positive side. What is the probability of getting this? So if you see that this is happening very rarely. Very rarely some data is crossing this green line, and very rarely some data is crossing this green line on the other side. So the chances of this data occurring at such extreme values is pretty low, and this is what it's saying. This is what it means. So on the green axis, or if you look at this side, the probability of crossing this green threshold is very low. It's close to zero almost, and we can very confidently say that you will not find any data which is beyond 23 or 24. A data like that will not be found in such kind of randomness. This is how we can draw inferences from even random data, and such data insights can help us in designing systems. It can help us take control. It can help us draw a lot of inferences. For example, let's say if we pick up all the people who have completed their undergraduate courses or graduate courses in a city, say Houston, we are randomly picking up people, and we are just trying to figure out that after doing the graduation, how many people have undertaken academic or professional courses. So that's our random data set, and we start randomly serving the people, and we figure out that some people have done 2 courses, some have done 20, some have done 7, some have done 11, things like that. We are randomly getting this data. And when we plot this data, and if it's following a normal bell curve, which is what is called as Gaussian distribution or normal curve, you will find that most of the people will have a tendency of falling in the mean. That means you take all the people, take an average of all the number of courses that they have done, and then you pick up any random person from that city. The probability is that he'll be very close to have completed about 10 courses. Because the probability of that is extremely high. It will be very rare that you'll find somebody who has completed more than 25 courses, or it will also be very difficult to find somebody who has done no course. The probability of that is quite low. So even in this randomness, we can draw inferences which will help us in take better decisions, which will help us design better systems. So this is how it is to be interpreted.